Alright, in this video we're going to do 6-2, the law of cosines. This will be day 1 of a 3-day lesson. And we'll just hit the first bullet point here. Use this law of cosines to solve oblique triangles. These will be the cases side, 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 and side, angle, side. In another video, we'll look at modeling and solving real-life problems with the law of cosines. And then in day 3, we'll see an area formula, Heron's area formula, based on the law of cosines. And the book goes on to say, 2 cases remain in the list of conditions needed to solve an oblique triangle, side, 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 and side, angle, side. When you're given all 3 sides, or 2 sides in the included angle, you cannot solve the triangle using the law of sines alone. In such cases, we're going to have to use a law of cosines. And here we see it in 2 forms. On the left is standard form. On the right is a different form if we solve for these angles here. Let's look at standard form first. Notice we got 3 variations. We have a squared equals b squared plus c squared in the first one. Over here, the only thing that's different, we've switched places of a couple of them. Now it's b squared is equal to a squared plus c squared. And finally, c squared is equal to a squared plus b squared. These all look a lot like the good old Pythagorean theorem. A squared plus b squared equals c squared. Remember, in the Pythagorean theorem, this was always the hypotenuse because we were dealing with a right triangle. Now we're dealing with oblique triangles. They're not right anymore, so C is no longer a hypotenuse. These are just, sides of a triangle. If you are solving a triangle for an unknown side, you want to use the standard form because these are what the lowercase letters represent. So these are for solving for a side of a triangle. And let's continue to look at these. Again, the beginning part here looks a lot like the Pythagorean theorem. We're just moving the a's and b's and c's into different places, but it's always addition over here. Now let's look at the rest of it. Each of them then has a minus 2, minus 2, minus 2, and then here are 2 more sides, the same sides here. We have b squared and c squared added here. We have bc. Here's a and c, ac, ab, AB. And then finally, the last piece of the puzzle here is the cos of an angle. The cos of, and that'll be the same angle across from this side. In this standard form, this is side A, that length squared. Over here, we'll have cos of angle A. This is side B squared. This will be cos of B. Side C squared, cos of C. So depending on if you want to solve for side A or side B or C of a triangle, you would use these different standard forms of the law of cosines. Now, if we solve this and get this cos of A by itself, move these things to the other side, divide through, we get this alternate form. We use these when we want to solve for an angle. Solve for an angle. So our numerator in each of them are the 2 sides squared and added together, squared and added up, and then we minus that last side, side quantity squared. And then the denominator is 2 times these sides that were added upstairs, B and C, BC, AC, AC. You see the pattern. So again, depending on if we want to solve for a side, we use the standard form. If we're solving for an angle, might want to use the alternate form. Let's try it out here. Example 1, given 3 sides, side, 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 find all 3 angles. Let me take a minute here to note that when you're given all 3 sides of a triangle, the angles are locked in. There's only ever going to be one possible triangle. So we never need to check for a second possible triangle. Only one triangle possible. Because if I gave you 3 sticks of length 8, 14, and 9, you could assemble them into a triangle. And as you assembled those sides together, the angles would sort of fall into place and be locked into place. So we never have to check for our second triangle. Now, something else of pretty good importance here, when we're dealing with a side, side, side scenario, always solve for the largest angle first. And how do we know which angle is going to be the largest angle? We'll look for the largest side. The biggest angle will be across from the longest side. So here we can see quite easily that B is 19. That's the biggest side on the triangle. That means angle B is going to be the largest angle. Always solve for the largest angle first. If there's an obtuse angle, we want to get it out of the way. And in a triangle, you can only have one obtuse angle at maximum. So if there is one there, we're going to flush it out right now. So we're going to do the law of cosines. We'll set up the alternate form. Since we want to find angle B, we're going to use this form here, cos of B. And that'll be the cos of angle B is equal to a squared plus c squared minus b squared. And then our denominator will be 2 times a times c. So there we can just punch that in our calculator, and we'll get this as a decimal between 1 and -1, and we'll cos inverse. If we punch everything in the calculator correctly, we're going to get cos of b is approximately -0.45809. And then, like I just said, we're going to cos inverse. Angle B is approximately, we're just going to round this to one decimal place for now, 116.8 degrees. 116.8. So now I'm going to go up to my triangle here. I'm going to just draw that in, 116.8. Now we could, if we wanted to, use the law of cosines to set up to solve for angles A and C. Or now that we've got a side and the angle across from it, we can go back to the law of sines. So we could set up 19 divided by the sine of 116.8. We could solve for either of those. I think I'll go for angle A. So that would be equal to 8 over the sine of A. And this law of sines, this is old news from the last section. We're going to cross multiply here. We're going to have angle A. When it's all said and done, the sine inverse of 8 times the sine of 116.8 divided by 19. So we would punch this in our calculator, get that as a decimal, do the good old sine inverse, and we get angle A is approximately 22.1. Now to get angle C, we could do law of cos, we could do law of sines again, or we could just subtract from 180. 180 minus the two angles that we already got, angle C is 41.1 degrees. 41.1 degrees. And there we solved the side case of a triangle. Again, when it's side, there is never the possibility of a second triangle. So here's a practice problem for you. If you're getting sick of listening to me after you try to solve it, you can go here to the audio book or the ebook and click on that. It'll take you to the English or Spanish solution of that. So pause the video, solve the triangle, and then start it back up and see if you got it. Okay, first thing I'm going to label my triangle. Let's see, side A is 6, B is 8, C is 12, biggest side is 12, so we will be going after angle C. So let's see, the cos of angle C is going to be a squared plus b squared minus c squared over 2 times a times b. So there's our fraction is set up. We get that as a decimal in our calculators, and then cos inverse angle C is approximately 117.3. So it was an obtuse angle, and we found it right away. 117.3. All right, now that we've got an angle and the side across from it, from here I just did law of sines. 12 over the sine of that angle is equal to 6 over the sine of A. And we cross multiply, get sine by itself, and then sine inverse. If you did everything right, angle A is about 26.4. And to find B, we just subtract from 180, and we get 36.3 degrees. Side, 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 there is only one triangle possible. Another book says, do you see why it's wise to find that largest angle first in the example? Knowing the cos of an angle, we can determine whether that angle is acute or obtuse. So if cosine is positive, we're in between 0 and 90 degrees in the first quadrant. Think back here, here's our quadrants in the plane. And cosine values are the x values. So when we start opening up an angle, here we are in positive x territory, and we're going to be between 0 and 90 degrees. When cosine changes negative, that would be over here when our x values change negative, that'll give us any angle between 90 and 180 for an obtuse angle. And remember, a triangle can only have one obtuse angle at most, so if there is one there, we want to find it right away. Example 2, now it's side angle side. If we look at the picture here, we have two sides and the angle between them. So, to set up our first fraction in the law of sines, we need a complete fraction. Here, we're missing something from everything. From 25 degrees, we're missing the side. From side B, we're missing angle B. From side C, we're missing angle C. So the law of sines won't cut it, at least to get us started. But we do have the law of cos, and the law of cos we can solve for any missing side that we want. So here we want to find this side A, so we can start to use the law of sines. And the law of cos here will be a squared is equal to b squared plus c squared minus 2b times c times the cos of angle A. So there it is with the numbers all plugged in. A word of caution if you're doing this on a calculator, especially like a TI-30. I'm real cautious right here when we're doing this subtraction. On a TI-30, I would type in 9 squared plus 12 squared minus, and then hit the left parenthesis. That's going to zero out the display because now you're going to work on what's inside. And I would personally start here. I'd do 25 and hit the cos key, and then times 12 times 9 times 2, and then you close the parenthesis, and that will show what happened inside. From there, you got to hit the equals key once more to actually do that subtraction. So be cautious here when you're doing these on a calculator. TI-89's not so much because it'll take all the order of operations into account. So here, if we do all the work to the right of equals, we're going to get about 29.2375. Very common mistake I see. People stop right here and put that in as the side length. Remember in law of cos, these are always squared. So this is a squared is equal to this. We got to hit the square root key. And we get A is approximately 5.4072. Let's just round that to about 5.4. So side A is 5.4. Oops, 5.4. And I guess they did give us units here. 5.4 meters. All right, law of cos, we've used it once, and usually once is plenty enough. Now we can just do the law of sines. I think I went after angle B next. 5.4 over the sine of 25 is equal to 9 over the sine of angle B. And again, law of sines, this is old news. If we do all the algebra, we're going to get angle B is equal to the sine inverse of 9 times sine 25 divided by 5.4. So we would punch in the stuff here in the parenthesis, get our decimal, sine inverse that, and we're going to get B, angle B, is approximately 44.7 degrees. So angle B, 44.7. Now, since this is side angle side, there could be a second possible triangle out there. As soon as we found this missing side, that missing side will also be true on the second triangle if there's one out there. So let's set up this possible second triangle. It'll have the same given info, 25 degrees here for angle A. Side B is 9 meters. Side C is 12. Here's angle C up top and angle B. Remember when we were doing this in the other section, as soon as we found a missing angle, our first missing angle, we immediately check for the possible second triangle. So we found the side here, but as soon as we found this missing angle B, we want to check for the second other possible triangle. Just like we did when we were doing this for Law of Sines, it's just the supplement. We're going to do 180 minus this angle B, 44.7, and that'll tell us this other triangle, possible triangle's angle B here. And when we subtract that, we get 135.3. 135.3. Ooh, and I should have put in there right away, when we found this 5.4, that is also true on both triangles if two triangles exist. All right, now look at what we're left with. Our triangles are almost done. We're just missing angle C. And of course, we're now down to the easiest way to find a missing angle, 180 minus the angles that we already have. So in this first triangle here, this angle C, 180 minus 25 minus the 44.7, that's 110.3 degrees. Over here in the other triangle, 180 minus 25 minus 135.3 is 19.7. Uh-oh. We have two triangles. Is this possible? Well, now we're really going to have to think back to the laws of geometry, and one of these triangles probably is not going to make sense. Remember, the biggest angle is across from the biggest side. So here is our biggest angle, 110. It is across from the biggest side, 12. Here's our smallest angle, 25. It is across from the smallest side, 5.4. Let's check this other triangle. Biggest angle here is 135. That's even bigger than the triangle on the left. But the biggest side here is still 12. So that doesn't make sense. Our smallest angle is 19.7. But that's not across from the smallest side. So even though there's 180 degrees in those three angles and the sides are all there, the triangle does not make geometric sense. So the first, or the triangle over here on the left, is the one that we were looking for. Okay, one more here, got our last checkpoint. So give this here a shot. You know, always, and don't forget to check for the second triangle. And actually, let me get this set up here. Remember, the given stuff will be true on both triangles. And let me clone this triangle real quick. If there are two triangles there, the given info is always true for both. So this angle A is 80 degrees. B is 16, that's side length. C is 12. So what we're going to do here, first solve for side A, so we can set up a law of sines, and then it doesn't really matter if you want to go for angle B first or angle C first. It doesn't matter. You know, the good triangle will be the good triangle, the bad triangle will be the bad triangle. But either way, if you solve for angle B first, always check for the second triangle's B down here. If you solve for C first, go for that angle C in the second triangle also. So pause the video, try to solve that, and then start it back up, see if you got it right. Okay, so let's see, for this one, to find this missing side A squared equals, using our new law of cos standard form, it's going to be 12 squared plus 16 squared minus 2 times 12 times 16 times the cos of 80 degrees. And we punch that in the calculator. Again, don't forget to hit that square root key. You should get A as approximately, let's take this to 2 decimal spots, 18.26. 18.26. So that's our missing side, 18.26. That is also true, again, on both triangles if two triangles exist. Now here, just to pick one, I went for angle B next. Again, if you went for angle C, you're going to get a different bad triangle, but your good answer should always be your good answer. So here I did, what would that be, 18.26 over the sine of 80 is equal to 16 over sine B. Cross multiply, sine inverse, angle B should be approximately 59.66. So up here, 59.66. As soon as I find angle B here, I'm going to check for my second angle B. 180 minus this angle B is 124.4. Now in the example, there were enough more degrees to go around and we come up with a second triangle, but it did not make sense. Here, we're already over 200 degrees. Here, this is 80 at 120, and you're already over 200, so there is no second triangle at all. If we come back up to the first one we started here, the only thing missing now is angle C. Subtract the other two angles from 180, and we get 40.34. 30.34. Alrighty. Here is the homework assignment. Remember, this is on WebAssign. The even problems are on WebAssign. We will do these odd problems in class. I'll make another video with those odd problems because they do help you with the even problems. If you do have internet issues or if there's problems with the WebAssign site itself, you can always do these even problems in the book found on page 413.